Hello everyone, my name is Federico. I'm a PhD student at the University of Oxford and I'm a teaching assistant for the Geometric Deep Learning course, which will be going on around now. What I want to do is make videos as kind of supplementary material for the course, but I also want to keep them self-contained. So if you're not taking the course, or if you're if you have no idea what's going on in the course, hopefully this will be helpful regardless. So here we have a graph, and the graph will be kind of our main object of study, at least for these videos. What we want to talk about is graph neural networks. And we will start with the most basic models, so we'll start nice and slow, and then kind of ramp up as we go. So today we'll start with the graph convolutional network, which is probably the most kind of classic graph neural network model. It's very powerful, very used, and extremely popular. And the problem setup we have is pretty much we have a graph, and this could be any type of graph, so molecular graph or a social network graph or a road network graph or something. And then at each node, what we also have is a vector. So this will be this xi, which will be like a d-dimensional vector. So we have d-dimensional vectors on every node, and you can imagine if this is, for example, social network graph, then this will be like my node, and this will be like my features, and then this will be like your node. And this edge means that like we're pretty much friends on this social network, and if there's no edge, it means we're not friends on this social network. And you can imagine like your features could be like this kind of vector where the first entry will be like your age, the second one will be like how many friends you have, which corresponds to the degree, and so on and so forth. So depending on the problem, you can have different features and different feature vector sizes, of course, and so on. Now, what we want to do is put all these features together in a nice way, and this will be through this feature vector matrix X. So you can imagine X as like having row vectors of all these features. So this will be like your x1 and so on until like xn. So this matrix will be n by d. Right. And what we want to do is kind of build up on this by actually we want to build up all the way until we retrieve the graph convolutional network model, or at least like one way one could think of deriving this model, and it will be all very intuitive, right? So to derive the graph convolutional network model, we'll need this X, which is kind of a way to summarize all our information. We'll also need A. So A is our adjacency matrix, and we can look at it element wise. So A will be will have entry 1 if I is connected to J in the graph, and 0 otherwise, right? So A pretty much looks something like this. So it'll be an n by n matrix. So imagine these ij's, you're kind of giving a labeling over these nodes. So this is an arbitrary labeling, and so on. So each node you give a label, and then ij will have like some entries, which will be it'll be a Boolean matrix, and if this entry here, for instance, is entry ij is equal to 1, it means that there's a connection between I and j. So for example, the entry 1 and 2 in this matrix will be equal to 1, but let's say 3 is this node here, the entry 1, 3 will be 0 in this adjacency matrix. Okay, and now what we want to do is find a way to do something called a convolution over a graph. So you can imagine that at each node, we want to kind of take into consideration information which is in its immediate neighborhood. So in this social network, for example, let's say we're trying to figure out whether a specific node is a scammer or not, right? So instead of considering this xi, which would be like the features of the person itself, to figure out if this person is a scammer, we want to consider xi and all of the immediate neighbors of xi, right? And this is called a convolution over a graph. And this is how we can do this. So we can simply multiply a and x together. And what this results in, and you can try to convince yourself of this if you literally carry out this multiplication, and this might be actually a good exercise, is that like you're still constructing an n by d matrix, but now the row of this matrix, instead of being x1, will be the sum over all the neighbors of x1, right? And this is exactly what we're trying to do. We're trying to convolve over this. Now, there's an issue here. Imagine that all these features are positive, then nodes which have more neighbors, right, and a node which has a higher degree will have more sums, and so it will likely have a larger entry. And this is actually very much not intended, right? Like this could be like this pretty much makes the degree an important factor in your classification, which is likely not always the case. And then you just simply wouldn't want to have this kind of behavior, right? So it's natural here to want to normalize this. And to normalize this, what we do is we can, for example, build this degree matrix D. And D is simply a diagonal matrix, but the ith entry will be the degree of the node I, right? So yeah, so it's quite a simple matrix, but we can use this to diagonal or to normalize this kind of structure, right? Because like the ultimate plan is that we actually want to build a neural network out of this, so a graph neural network out of this. So imagine now if this AX, right, we could, for example, add a weight matrix here, and we could add like a ReLU here, right? Now, the effect of this would be effectively that we are kind of doing this behavior here, right? So if maybe let me write it here, right? Like this would be some kind of nonlinearity over this sum of xj's and a weight matrix. So this is actually a very nice form for our graph neural network. So we're pretty much taking all of the xj's and then passing them through some learnable matrix, and then we're also passing them through nonlinearity, right? So if we could just fix this issue, right, with the summation, we'd be at a very good spot. So we can do this in a couple ways. One way could be by multiplying by d inverse this dAx, right? So if we have this, effectively what this does to the summation is it normalizes by the degree of information, right? So like d inverse, since this is diagonal, all the entries would be like 1 over di, right? So this operation is pretty much just normalizing this aggregation here, and this is nice, and it likely will work as well. But what is done more commonly in practice is normalizing in a slightly different way, is normalizing on both sides by d to the minus a half, right? So this is what's done more in practice, and it's because like this normalization is slightly more interesting. So here you can imagine as behaving as like 1 over di, right? This normalization. Here instead it behaves as 1 over the square root of di dj. So it's a slightly different normalization, but yeah, this tends to be preferred in practice. So empirically it tends to perform better usually, and so on. So again, what we want to do, like we came back to our problem, like we have our convolutions here, but the summation is a bit problematic. So we want to kind of normalize this, and we've proposed one way to normalize it, but then one preferred way, which is like kind of the winner. And then what we want to do is similar to how we were discussing, is we can add nonlinearities, and we can add like a weight matrix to kind of give this more of a neural network feel, right? And this actually leads already to the Graph Convolutional Network model, which is this one right here. And actually, I forgot to add one thing. Now, in this sum, when we're convolving, oh my god, when we're convolving, right, we are pretty much convolving over the neighbors of xi, right? So like if we consider xi, so if this is like xi, we are pretty much summing over all the neighbors in some way, and then we have like some kind of a normalization constant here, right? Like some 1 over Cij. But let me just put it here so it's like easier to see. So this is like just a scalar that's kind of normalizing everything. But like the one of the issues that if we simply use A is that we will be only considering the neighbors usually, right? So if A does not contain elements on the diagonal, then we will never be considering the node itself. So actually what we do is we simply construct usually this A hat, which is simply A plus the identity matrix. And what this does is it pretty much just adds a 1 to all the diagonal to the entire diagonal of A. And this is kind of like adding a self loop at each node, right? And what happens now is that now this ij will also include the case where like I is connected to I, which will be effectively like here your hi will also include like adding this I here will be kind of like doing like plus xi, right? So like plus the node itself by adding this thing. So this is actually it. So again, all we did was we started with our ax, and we said, okay, this is a nice way to convolve over this graph. And then we found out some problems. So the first problem was that, well, we want to consider when we're computing this hi, we want to consider the node itself. So we fix this by adding this diagonal entry, right? This identity matrix. And then we also wanted to fix the fact that this sum is like not very well normalized, and this was done by multiplying a on both sides by this kind of normalization factor. And this is it. This is the graph convolutional network model. We have this w, which is learnable, and then we have this non-linearity, which usually you take to be like, for example, ReLU, and this will construct our feature vector h. So we can view this in another form, which is maybe more intuitive. So this is like our final GCN model. It will be some hi will be the sum over all your ij's. Again, remember that this sum includes the node xi instead. So, and then it will be again this normalization factor, which will be di dj xj w, and this is it, right? And then also the nonlinearity. So you can imagine this intuitively. Like what we're doing is for each xi, we are first of all kind of transforming these xi's by some learnable weight matrix. Then we're also normalizing them, summing over all of these, and then putting them through a nonlinearity. And this is considered to be like a single layer of a graph convolutional network, and it's an extremely powerful construction. Now, notice that well, if we look at kind of the dimensionality of h, right? So all of these, like all of this, will be n by n. This we said will be n by d, and this w can be d by d prime, for instance, right? So h becomes n by d prime. Effectively, what we're doing is we're taking some kind of signal over the graph xi. So some kind of, each node will have a d-dimensional signal, and then we're turning it into a d prime dimensional signal, so a different dimension now, by passing it through some weight matrices, normalization, and so on. So locally convolving and aggregating this information. Now, why are we taking, this is kind of an interesting question, why is w on this side and not on this side? Well, this kind of relates to this idea of permutation equivariance, and this is maybe, especially with the course, you can kind of try to figure out why multiplying w from the left would actually break permutation equivariance. So this is maybe like a simple thing that you can check yourself. So actually this is just to say that like there are all these little things which make these models work, and these inductive biases which one needs to kind of keep track of. So I hope you enjoyed this video. This was a quick kind of introduction to graph convolutional networks. The next video will be on graph attention networks, and that should prepare you for the practical sheet. So thank you for watching, and see you in the next one.